All right, this is part 2 of 4.1 on finding equations of exponential functions. So, oh, there we go. Sometimes we don't know the growth rate, but instead we know some kind of input and output pairs of values. And this actually still allows us to construct an exponential function. So looking at this given example, in 2009, 80 deer had been reintroduced to a wildlife refuge area from which the population had previously been hunted to elimination. By 2015, the population had grown to 180 deer. If this population grows exponentially, find a formula for the function. So let's say t is years after 2009. If t is years after 2009, then we have two input-output pairs here, right? We have the pair, that means that in 2009, we're in t equals 0. And in 2009, there were 80 deer. In 2015, which is 6 years after 2009, there were 180 deer. Notice that this means that our initial value is 80, right? Because at t equals 0, we have 80 deer. So this already gives us the equation. F of t equals 80 times b to the t power. Now if we substitute in our second input-output pair, we can solve for b. So if I have 180 equals 80 times b to the 6th power, I can divide both sides by 80. And I get that b to the 6th power is equal to 9/4. 180 over 8 simplifies to 9/4. To solve for b here, I have to take the 6th root of both sides. This gives me that b is the 6th root of 9/4, which is about 1.1447. And this gives me that f of t is, our initial value was 80, right? We had 80 times b to the t. This is 80 times 1.1447 to the t power. If I wanted to find the growth rate here, remember that b is just 1 plus r. This is 1.1447. This gives me that r is 0.1447 or 14.47%. That's my growth rate. Let's look at another example. Find a formula for the exponential function passing through the points -2, 6 and 2, 1. Here, we don't have an initial value, so we have to take a slightly different approach to solving for this. We're going to have to solve for one of our variables and then plug that substitution in for that variable in another equation. We'll see what that looks like in just a second here. So if I remember that I have an equation in the form of f of x equals a times b to the x power. If I substitute in the point -2, 6, this gives me that 6 is equal to a times b to the -2. If I substitute in the point 2, 1, I get that 1 is equal to a times b to the first power, or second power, sorry. Let's see. In this first one, what do we have here? We have that 6 is equal to, so b to the -2 power is the same thing as b squared, but in the denominator. So if I have a negative power, I can flip that term to the other side of a fraction and make the power positive. So these two things are equivalent then. This actually lets me solve for a. If I multiply both sides by b squared here, this gives me that a is equal to 6b squared. Then in this other equation, everywhere I see an a, I can write 6b squared. So now I can solve for b very easily. Right? This means that 1 is equal to 6b to the 4th power. Divide both sides by 6. And I get that b to the 4th power is 1/6. Now I can take the 4th root of both sides. This gives me that b is about 0.6389. And remember that a is 6b squared. So this is 6 times 0.6389 squared, which means that a is about 2.4492. And if I plug a and b into my equation, this gets me that f of x is 2.4492 times 0.6389 to the x power. And here we have a graph example. Let's find an equation for the exponential function graphed here. So the first thing that we have to do is find some points that this clearly passes through. To me, let's see, the point 1, 2 and the point 3, 4 stand out here. Oh, and I suppose the point negative 1, 1, right, passes through all of these points. We only need 2 of these points. So we might as well use these first 2. Let's go ahead and use these first 2. Any 2 would work. So if I substitute in the point 1, 2, I get that 2 is equal to a times b to the first. If I substitute in the point 3, 4, I get that 4 is equal to a times b cubed, right? Again, this is just coming from our generic f of x equals a times b to the x. This actually lets me really easily solve for one of these variables, right? For instance, in this first equation, b to the first is just b. I can solve for a or b really easily here. Let's solve for a. We'll divide both sides by b, and I get that a is just 2 over b. So in this right-hand equation, everywhere I see an a, I'm going to replace it with a 2 over b. Let's see. 2 over b times b squared is 2, or 2 over b times b cubed, rather, is 2b squared. I divide both sides by 2. I get that 2 is equal to b squared. And I'm taking the square root of both sides here. Now, normally I'd have b as plus or minus root 2. But because we're limiting ourselves to positive values for b, b is just going to be square root of 2, the positive square root of 2. And we said that a was 2 divided by b. So if a is 2 divided by b, then a is 2 divided by the square root of 2, which is the square root of 2. So our final equation here is f of x equals square root of 2 times square root of 2 to the x power. And once again, I'll split the recording here so we can move on to compound interest in the next video.